All right, so today we'll have the BES module tutorial. That's beam emission spectroscopy. We have Matt Creedy who will be presenting it. Take it away.
All right, thanks, Sterling. All right, so yes, I'll be talking about the BES module in OMFIT. Before I get into that, I'll just show one slide or two real quick on what beam emission spectroscopy is for people who aren't aware. So beam emission spectroscopy is a diagnostic on D3D and several other tokamaks around the world now, NSTXU, HL2A, MAST, etc. That basically measures density fluctuations in the plasma in a spatially localized manner. And so common approaches, we usually have big arrays of BES with dozens of channels arranged in 2x2D grids in the plasma, so we can actually measure turbulence across the spatial domain of the plasma. And so the basic idea is, I'm not going to get into details of too much, but basically we're measuring the N=3 to N=2 atomic transition of the deuterium atoms that are inside the neutral beam. And because the neutral beam is traveling at much higher velocity than the background plasma, it's Doppler shifted compared to the normal plasma d-alpha emission. And so we measure just the part of the spectrum that comes from the neutral beam. And if you work through the atomic physics, it turns out the intensity of that emission line is proportional to the density of the plasma. And so just by measuring this emission line with very high precision, low noise amplifiers, we basically measure fluctuations in plasma density. And because I'm a diagnostician, I have to throw up like the picture of what the diagnostic looks like. So just a crazy mess of amplifiers, vacuum, cryogenically chilled amplifiers, fibers, signal processing electronics, you name it. All right, so with that background out of the way, let's get into how the BES module in OMFIT works. So go ahead and this just launched up just a fresh OMFIT session. So go ahead and import the BES module. There we go. All right, BES is nice, and it's nice that it begins with B. It's always near the top. All right, and just double click on BES to open up the GUI, and then okay, there we go. All right, so this is the main GUI, and basically this module is a set of different analysis tools that are suited for analyzing turbulence data, and they're arranged so it's basically arranged by tab in this GUI. So you have load data tab, which of course loads the data for a particular shot or machine of interest, and then basically these analyses are organized from left to right in terms of increasing complexity. So spectrograms is kind of a low order analysis. That's kind of the first thing you'd want to look at when you're starting to analyze turbulence data. And then you move to the right, you do more sophisticated analysis. You start looking at cross spectra, cross correlations, and then at the most sophisticated analysis, which only a few people in the BES group really run, is called velocimetry. And I'll get into the details of all of this, but there's a kind of workflow from left to right here, because you use results from these first order analyses to set parameters in the higher order analyses. So to start off with, so we have two, right now the BES module supports two machines, D3D and NSTXU. Mostly we just used it for D3D data. So I'm going to be walking through a shot, basically the analysis of turbulence data from one of the shots I've been studying as part of my thesis work. So this is, for example, this shot is 171472. So I will open up the tree, the BES tree over here, and in this inputs directory, you can see here there's a folder for fast and slow data, which is currently empty. So when I press load BES data, you can now see that this fast and slow trees have been populated with 64. There's 64 channels for the D3 system. So basically 64 different MDS value references to the 64 different BES channels. And just briefly, the reason we separate fast and slow data is kind of historical for D3D, but basically that the fast data is the actual turbulent part, and the slow data is this fast data is sampled at megahertz speeds. The slow data is kilohertz level speeds, And that gives you sort of how the mean evolution, how the slow evolution of the density evolves throughout the plasma. So it's sort of the turbulence part and the mean part. Okay, so you load the BES data using that button. And then the second half of this load data tab basically has a nice little plotting utility to show where how the BES channels are arranged in the edge of the plasma. It's kind of a replacement for, or not replacement, but has the functionality that EFIT viewer does. So, for example, so you set the same shot number, and the time period I'm going to be analyzing is around 2,000 milliseconds. So we'll plot the EFIT at that time. And I'll just drag all this out of the way. And so this basically just shows the arrangement of BES channels. So this is Z machine coordinates, Z vertical centimeters, major radius. The solid black line is the separation of the plasma. So for this shot, BES was located near the edge of the plasma with a few channels moving into the scrape-off layer. The array is translatable, so some shots it could be located deep in the core. Kind of depends on what shot you're looking at. And you can see that, so it has the BES for the shot was arranged in 8x8 configuration, and all the channel numbers are labeled here. So I'll be referring back to this this little plot a lot, and as I go through analyses to kind of locate where channels are. And the other thing is that when you load an EFIT, it uses this EFIT to map the BES channel machine coordinates into flux coordinates. So now every single channel has both its RZ coordinate and its rho and psi coordinates. So that's useful for plotting later down the line. Okay, so the first analysis that you usually use when you're studying turbulence data is just looking at spectrograms. So if any of you are familiar with the inspect tool at D3D, this is basically the same functionality as inspect. So all this basically does is it gives you a kind of a qualitative overview of how the turbulence spectra is evolving over time throughout the shot. So for example, so we'll pick, for example, channel 45. Channel 45 is near the midplane, and it's about 2 centimeters inside the separatrix. So if we want to see what the turbulence looks like, channel 45, type in channel 45 for both the channel 1 and channel 2, because it can do both auto and cross spectrograms. So that's kind of a detail. And there's a few settings here. These defaults are good for the vast majority of analyses that you care about, and if you very rarely would have to fiddle with these. The filter settings are not super important for spectrograms, but will be for later analyses. And so let's just plot spectrogram, see what it looks like. So because the BES data is sampled at really high speed, we produce a lot of data per shot. So actually loading in data sometimes can take a while. So it takes about 10 seconds per channel that you have to load in. But so looking at one channel is not too bad. So here's a spectrogram. I'll just go ahead and blow this up. So this is basically telling you what the spectrum of the turbulence is, frequency in the y-axis, and how it evolves in time throughout this approximately 6-second shot. So this data, basically this is a shot that transitions from L mode to H mode and back again several times. So this period here from say 1200 milliseconds to 2200 milliseconds is L mode. So you can see there's very high turbulence amplitudes. And in fact, the turbulence is the peak location of the turbulence you can see is actually decaying frequency as you move forward in time. Goes into H mode, the turbulence amplitudes drop dramatically. That's a standard feature of H mode. And then you can actually see that this tearing mode grows up toward the end of this H mode and causes it to back transition to L mode. So you get L mode again, high turbulence, then it goes back in H mode, back in L mode. So this it's a tool for looking qualitatively at what the turbulence is doing. And the main utility of it is for identifying time windows where the turbulence is stationary, which you can use for the high order analyses that I'll be talking about next. So for this tutorial, I'm going to be examining this time window here from about 2157 to 2257. So this is a time period right before an L to H transition, which is what I researched for my graduate thesis. That's why I'm going through this example. But you can see over this time window, the turbulence is relatively stationary. So that's the time window we'll pick.
So the data source was fast, but you only were going up to 200 kilohertz, right?
Yes, so that's because, so if you go on this plot settings tab, you can change the color map. I like Inferno, but you can use any color map you want. And here I have the frequency limits. I have a default set from 0 to 200. So the data, since we sample at a megahertz, you can go all the way up to 500. And you see that basically because the turbulence spectrum only extends out to about 100, there's nothing up there. But for other shots with more rotation, higher frequency, yeah, you would want to change that limit. And you can also change that limit once you have the figure generated. If you right-click anywhere on the figure, you can change the Y-limit manually. So you can either do that through the GUI or by right-clicking on the figure. And then you can also change the color scale limits and whether or not it's a log or linear axis there. All right, so you looked at the spectrogram. You have a qualitative idea of how the turbulence is evolving throughout the shot. And so I noticed that that time window from 2157 to 2257 would be interesting for further analysis. So now we'll look at cross spectra, which is kind of the next step, next more sophisticated step in the analysis train. So I'll type in 2157 to 2257 milliseconds for the analysis time window. And cross spectra are basically spectra. Basically, they measure the portion of the spectrum and the signal that's similar between two channels. And so a common trick we use for BES, and I think many turbulence diagnostics use this, is that you basically look at cross spectra between two channels that are adjacent to each other in the plasma. So the reason you do this is because, like say for example, I picked channel 45 and 53. These channels are only 1 centimeter apart from each other, so they're sampling very similar turbulence. However, each of these channels has different, has basically statistically independent noise. So the noise that BES picks up is a combination of photon noise that's kind of irreducible and electronic noise in the amplifiers. And so by taking a cross spectra between two neighboring channels that are sampling the same turbulence but have different noise, you effectively suppress the influence of noise on the final spectra that you care about. So we usually do polytally, like nearest neighbor polytally separated channels. So I'll pick channel 45 and 53 for this. So I'll type in, for the reference channel box, I'll type in channel 45. And then for the target channel box, I'll type in channel 53. I'll use that time window identified previously. Cross spectra are basically FFTs. Basically, the whole time record is binned up into segments. Each segment is Fourier transformed, and they're all averaged together. And that averaging process is what gives you this noise cancellation I just mentioned. And so these parameters are good default parameters for a lot of cases. The one you change most often is the number of points per segment. Basically, if you look at these, there's help boxes for most things. So this help box explains that there's basically a trade-off. The more points per segment you have, the less, basically the more noisy the spectrum will be, but the higher resolution it will be. So you have a trade-off between noise and resolution, and you can basically redo the spectrum analysis and change its value multiple times if you want to look at that. So I'll just use the defaults here.
You don't try to make those powers of 2 necessarily?
No, the power of 2 thing is just a numerical efficiency. It just makes the FFT faster, and for this, the FFTs in this are taking like a fraction of a second. So using a power of 2 versus 1,000 is like a negligible change in computation time. Plus, then it gives you nice spacing, because if you use 1,000, then your delta F is 1 kilohertz, so everything is nicely spaced. I like to use powers of 10. So I'll calculate the cross spectra. Again, it'll take a few seconds because it's loading in right now 6 seconds of 1 megahertz sample data.
You loaded data at the beginning that was only for.
So it's a little, so basically this module is designed to load the data lazily. So when you actually clicked load data on that tab, it didn't actually pull any data into memory. It basically just made references to where the data is stored in the MDS server. And so none of that data is actually loaded onto this computer or into the iris work node you're working on until you need it for an analysis. And the reason is because if you try to load all whole shots worth of data at once, it takes like 10 minutes, and then you're waiting 10 minutes when you only need to look at like 2 channels.
That makes sense.
So, okay, so So that cross spectra is done calculating. You can see the title up here. It mentions the shot, it mentions the channels you used in the time window. And there's a few tabs here. So there's basically three different cross spectral quantities. There's the cross power, which is basically a measure of the amplitude spectrum. There's the cross phase, which is a measure of the phase difference between these two polarly separated channels, like 45 and 53. And then there's the coherence, which tells you how, yeah, I'll get to that in a second. So if you look at this power spectrum, you can see the turbulence amplitudes are peaking around, about say 60 kilohertz. You look in the bottom right of the graph down here, you can see as I move my cursor around, it tells you the X and Y value. So I can just look at this and say, okay, peaks around 60 kilohertz. And you also see there's a second peak at lower frequency, somewhere around 5 kilohertz or so. So now if you look at the cross phase, this basically tells you what the phase angle is between these two channels as a function of frequency. And so here this phase is in radians, so it goes from negative pi to pi. And it basically looks more or less like a linear trend, slight rollover. And that's indicative that the turbulence is kind of propagating at a fixed velocity from one channel to the next, 4553 there. And so there's a lot of these cross-phase plots can get kind of complicated, and you can spend a lot of time kind of thinking about what they mean if they're not linear, but in this case where it's linear, it just basically means that turbulence is propagating uniformly from one channel to the next. And the final thing is the coherence.
There's directionality too. Obviously, the phase, like it's up or down. Like one direction is like the ion direction, and one's the electron.
Yeah.
Anyway. Yeah.
And then and the coherence basically tells you it's a measure of how coherent the two signals are at the two channels you entered 4553. So on this coherence plot, there's this dashed line plotted, which is basically the kind of minimum statistically significant coherence level. And so basically, if the coherence line is above this dashed line, that means that there is basically that it's saying that at that frequency the signal is not noise. There's actually some real common signal that's shared between the two channels. Might help if I go ahead and change the axes. So if I said plot up to 500 kilohertz, you can see that over the whole spectrum, basically the turbulence part of the spectrum extends from 0 frequency up to around 200 or so. And then from 200 to 500, the spectrum is dominated by noise, photon noise, electronic noise, what have you. These spikes are electronic resonances somewhere in the circuit, but they're well beyond the turbulence part of the spectrum, so not a problem at all. So I go back. So this basically tells you that everything from 0 to around 200 is legitimate turbulence signal, and we can use it in further analyses down the road. So. All right, so that's you look at one pair of channels, and that's useful for determining things like just what the spectra looks like. The next thing you might want to ask yourself is, what is the actual quantitative fluctuation amplitude? What's the delta n over n as a function of radius in this edge region? And so for that, you go into this derived settings tab. So down here you can see under cross spectra there are a bunch of different subsettings tabs. There's the settings for cross spectra itself. There are settings that for different filters you can apply. So actually, I'll go for one example is there's this beam noise filter. There's the neutral beams on D3D oscillate at a known frequency of 360 hertz, and if you don't enable this filter, you'll get a giant 360 hertz spike in your spectrum. And so this filter is designed to cancel that out. So pretty much always a good idea to have this guy enabled. Also, there's this transfer function correction, which is usually pretty small, but it is important for getting the quantitative delta n over n values right. So pretty much always want that one enabled too. And now this derived settings tab, this is basically the settings that determine how you calculate fluctuation amplitudes. So most of these don't need to be changed. The defaults are fine. And if you're really interested, of course, you can always click on the little question mark for a kind of description of what the setting does. But the only setting that you usually need to change is this analysis frequency limits. So I'll go back, I'll just replot that, that spectra I just showed. So if you look at the coherence, so this is basically saying there's coherent turbulent signal all the way from 0 kilohertz to around 200 kilohertz. And so if we want to calculate a delta n over n, we want to integrate over the portion of the spectrum where there's coherent signal. And so for this, I'll go ahead and in this analysis frequency limits box, I'll go ahead and type in 0 to 200. And so basically the way delta n over n, the way fluctuation amplitudes are calculated is by integrating this turbulent spectrum over the frequency range that you set. All right. And so now, let's say we want a profile of delta n over the edge region of the plasma. So we might want to start from the innermost part of the BES array, which is at a row value. You can see here, these dashed lines mark 10% row value. So this is row 0.9, this is row 0.8, this is row 1 separatrix. So we'll start at this one and move inward. So the way you can go into the GUI and type in just all the channels down the line. So 41, 42, 43, 44, 45, 46, 47, 48. And a nice shortcut trick, if you don't want to type in every channel number, is you can use Python, basic Python functions like range. So for this one, I'll just type in range 4957, and this will automatically generate a list going from 49 to 56. So it's a shortcut versus typing in everything. All right, and so I'll go ahead and start that calculation. It'll take about a minute to do because now it has to load in 16 channels of BES data, process it. And while that's calculating, I'll let me explain a little bit about what these settings mean down here. So the delta n over n calculation, you start by calculating basically what the actual, but when you integrate the spectrum that I showed, that tells you a delta I over I, basically what's the normalized fluctuation level of that atomic line that we're measuring. And then there's a coefficient that is based on atomic physics that relates the fluctuations of that intensity, of that line intensity, to fluctuations in the true plasma density. And normally that coefficient is usually about 1/2, and it varies very weakly with plasma parameters. But if you are, if you really want to make sure that you have that value as accurate as possible, you can type in different plasma parameters, which you'd get from Thomson data or other diagnostics. So you can type those in here, and it will calculate the actual value of that coefficient. So here I have kind of generic parameters for this plasma.
So using the same frequency range for all radii.
Yes.
Principle, that's a radially dependent quantity.
Yes, yeah. So when this is done calculating, you'll be able to see that you can actually, you can actually type in a set of ranges for each radius. So gloss over that part, but I'll show that in a second. Fortunately, when it's calculating things, the GUI is non-responsive, so wait for it to finish.
So you implemented that bully database, I guess, right into the.
Yep.
So can you describe some of these other entries there, the dark times?
Yeah, sure. So the dark times, for example, is basically used to set the basically it's a time period in the discharge where there's no light incident on the BES detectors, and so it's used to calibrate the slow signals so that 0 signal equals 0 light. That's not actually so important for D3D, but NSTX, based on the way that system is implemented, you usually have to change this parameter per shot just because of the way the BES system is started up on that machine. And then this photon noise subtraction, basically you type in a frequency range where you say that the turbulent spectrum is entirely dominated by photon noise. So I showed you guys earlier that basically above 200 kilohertz, the whole spectrum is photon noise. So you can type, the default is 350 to 450, usually pretty good. And we'll basically estimate the portion of the spectrum that is photon noise and subtract that off of the actual turbulent fluctuations. All right, so so now I did this analysis for 8 different pairs of BES channels spanning the full radial extent of the BES array. I already showed you here you can see all of the cross power spectra, all of the cross space spectra, and which look noisy. Basically, when the spectrum is coherent. For example, you saw the case I showed earlier is the purple one, 4553. So you can see at this radius, the turbulent spectrum is very broad. And then as you move outward toward the separatrix and also inward toward the core, turbulent spectrum becomes less broad. But the quantity you usually care about is this one, the fluctuation amplitude. So here you can see a plot of the density, normalized density fluctuation amplitudes across the whole array. And so actually I'll go ahead and quickly, right now it's on the x-axis is pair index. If you go to plot settings, there's a whole bunch of different settings you can kind of tweak to make the plots how you like them. I'll go ahead and set x-axis for pairs to row, and I'll X out of this graph and redo it. And one thing this module does behind, kind of under the hood, is it caches results of analyses. So you saw the first time I calculated that spectrum, it took like 2 minutes, but the second time it just popped up again because it saves the results of all your analyses. And it basically has some smart caching logic that whenever you ask to do a new analysis, it checks to see if there's an existing result that satisfies what you want. And then if there is, it just pops it out and you don't have to recalculate anything. So anyway, go to this fluctuation amplitude. Now that settings change, you can actually see now it's plotting this graph versus the row position. And so you can see this is a very standard result that fluctuation amplitudes tend to peak basically near the separatrix of the plasma. Okay, so I've gone over basically spectrograms and cross spectra. That's like probably 90% of what people usually want for BES analysis is fluctuation amplitudes and what direction the turbulence is propagating and that sort of thing. But I'll move on to more sophisticated analyses that are usually only run by people in the BES group. So the next one is cross correlations. And so before I get into, basically there's 4 important physics quantities that cross correlation analysis can give you. It can tell you what the phase velocity of the turbulence is, what the group velocity of the turbulence is. And then it can tell you correlation rates or correlation times and correlation lengths. So this is all more fundamental parameters of the turbulence itself. And so this is really important for my research. Involves a lot of kind of basic turbulence physics. And so this kind of analysis is very important for that. So for cross correlations, a lot of the time, for this analysis, for this example, I'll be calculating colloidal. I'm interested in colloidal velocities and colloidal correlation lengths. So I'll basically pick a specific column of BES data and analyze one column. And so for this example, I'll pick this column right here. It's the 6th column from the left, or the 3rd column from the right equivalently. This one that starts with channel 22 at the top and then goes down 30, 38, 46, so on and so forth. This is basically the channel that's just 1 centimeter inside the separatrix of the plasma. So go ahead. So the way you usually want to do this analysis is you want to pick one reference channel, probably at the end, either one of the either ends of the array. So I'll pick 22 as the reference channel, and then just go down and type in all the other channels in this column. 46, 54, 62, or 62, 6. And then I'll use the same analysis time window as previous. So that was 2157 to 2257. Okay. And then again, you have a bunch of subsettings that are specific for this cross correlation analysis. So this basically similar to the way cross spectra are done, cross correlations are calculated by splitting the data up into chunks, calculating cross correlation function for each chunk of data, and then averaging them all together. So this points per segment value here for the cross correlation is the same as the setting it was here for cross spectra. So usually this value is or something near it is pretty good. So the important part for cross correlation is you have to be very careful. You have to filter the data in a specific manner for you to get meaningful cross correlation results. And this is the part where using cross spectra is important to basically figuring out what bandpass filter frequencies you need to use to get valid cross correlation results. So again, you always want beam power supply filter enabled and the transfer function enabled. But now you need to pick a set of frequencies that that you want to isolate for calculating cross correlations. So this is where you want to go back to cross spectra. So I'll replot the cross spectra, which for some reason is not coming up immediately. There we go. All right, so actually, so because this was looking at a row of channels, so now I actually want, so I'm analyzing this column 22. I'm analyzing this column right here of data from 22 and down. So I actually want to look, before I do a cross correlation analysis, I want to actually compute the cross spectra for this entire column of data. So I'll go ahead and type in 22 as the reference channel. And again, I'll type in all the channels here. All right, and go, and that'll take a minute or so. Does anyone have any questions so far? It's a good time for.
I had a question. So when you are calculating the total, total line overhead, you said you had to input a frequency range.
Yeah.
That applies to all the channel pairs.
Yes.
What if some channel pairs have a narrower coherence than others?
Yeah. So when the GUI unlocks, I'll show you. Basically, you can set you can input instead of inputting a list of 2 numbers, you can input a list of two pair lists, and it'll basically break that out over each radio. So for example, if you're analyzing 3 different radio locations that had 3 different kind of coherent ranges, you would type in just separate lists for each one. I'll show you that in a second here.
Because that's not something you did before. You just had it.
I just use the same, yeah, which is quicker but not as accurate. So for any sort of publication, yeah, you want to narrow it down to a specific range.
Does it make that big a difference?
It depends a lot on the data you're looking at.
The filter range? Yeah, it can make a big difference.
All right, so just to show, before I get into that, just to show you how that works. So you actually, if you click on the help next to, so yeah, so this one, yeah. So if you click on this help button here next to the frequency range used for integration, it actually explains how this works. And so you can either input a single 2-element list, or you can input a list of 2-element lists that matches basically the number of pairs of channels you're using, and then it will flex.
Do you often go down all the way down to 0?
No, I usually stop at 1 or somewhere else.
Right. I'm scared of 0 frequency.
Yeah.
Weird things happen there.
Okay, so yeah, I'm looking at the cross spectra between basically for this column of data. So the important thing to look at here is the coherence. So you can see basically the blue is the coherence between a channel with itself, which is always identically 1. So that's why you don't even see a blue signal here. And then as you increase channel separation, basically just going down this color gradient, orange to green to red, purple, and so on, you can see that the coherence magnitude decreases because channels are farther away, so the turbulence is less coherent between these channels now, and the frequency range gets narrower and narrower, kind of monotonically all the way down to the coherence between 22 and 44, which I'll remind you is basically the coherence between the turbulence at the top of the array and the bottom of the array. All right, and so for the cross-correlation analysis, we want to isolate, you want to do as best a job as possible to isolate just the frequency range where there is a single mode of coherent signal. And so the single mode part is important. I kind of glossed over it before, but you can see in these spectra that there are in fact two modes. There's this mode at low frequency, and then there's a second mode at high frequency. When you're doing spectra, you just plot both of them at the same time. But when you're doing cross-correlation analysis, you need to make sure that you're isolating just a particular mode at a single time. So for this, for example, let's say I'm interested in the correlation properties of this higher frequency mode. So then I need to identify a frequency range over which to analyze that isolates this high frequency mode. And so currently right now for this, you do have to pick a single frequency for all of them. Basically it's a work in progress feature improvement I'm working on to use a set of frequencies for each pair, but let's go ahead and be a bit restrictive and say, so the lowest coherence range is this gray trace, the 22 to 14. That's the one that has looking at the cross spectra between the further separated channels. And so this one's coherent from about, let's say 40 kilohertz up to say 90 kilohertz. So I'll basically use 40, 90 kilohertz as my frequency range for the cross correlations, accepting the fact that for this, that's suitable for this pair, but for the others, you could probably broaden that a bit, but just be restrictive. So going back to the cross correlation tab and the filter settings, type in 40 to 90. And go ahead and move over to there, and then go ahead and start calculating. And again, because it's analyzing 8 channels of BES data, this will take a minute or two. So while that's analyzing, I'll go ahead and explain some of the settings in this derived settings tab. As I mentioned, the reason you do correlation analysis is to extract parameters like turbulence parameters, like correlation times and correlation lengths. And so these settings will make a little bit more sense when I show you some of the plots later, but these are basically settings that are usually, these are pretty good defaults. You shouldn't usually, well, you might not have to change them, but if basically the correlation times and correlation lengths are made by fitting model functions to the data, and these parameters you can kind of tweak. Like for example, you can tweak the initial guess of the fitting algorithm, which you sometimes need to do. So that'll make more sense. And the other important thing is that this channel separation direction setting, basically you have to set this either if you're looking at a column of data, you have to set it equal to Z because the channels are separated in the Z direction. And if you're looking at radial correlation, so if you're picking a row of BES channels, you need to set this setting equal to R. And that's basically just so the plots kind of know which direction you're going in. All right, so we got a bunch of graphs. Go ahead and I'll go back to these later, but just start with the main one first. So this is a graph of the correlation functions of the turbulence. So this blue one is the correlation function of the signal at channel 22 with itself. This is also called an autocorrelation function. And it's probably really hard to see what's going on here because there's so many. So, well, anyway, basically this function, it's basically an estimate of how, it's a measure of how correlated the turbulence is between two channels as a function of the times basically shifting one channel's data relative to the other. And so you can see that, so this autocorrelation function, this blue one, peaks at a time lag of 0. That basically, and that always is true for autocorrelation functions. That tells you that the turbulence is maximally correlated with itself when you don't shift that signal, respect to itself at all. So next is this. So if you move this orange trace is the correlation function between channel 22 and 30. So now you're looking at the correlation between two channels that are separated by about 1 centimeter. And you can see this correlation function peaks at a time lag of about, if you look at the bottom, like -3 microseconds. So that basically is telling you that it's taking about -3 microseconds, or the directionality matters. So about 3 microseconds for the turbulence to propagate from channel 22 to channel 23. And you can see as you increase spatial separation, going from orange to green to red, the peak of this correlation function shifts outwards in time. And that just reflects the fact that it takes longer for the turbulence to propagate between the reference channel 22 at the top of the array and the channel you care about. And so these correlation basically parameters from this correlation function, these correlation functions are used to estimate the actual properties of the turbulence you care about. So you can base, these are all plotting settings for the correlation functions that you can play around with. For example, here I'm actually showing I'm showing both the correlation functions and their envelopes, so you can just show, or I should have done this actually originally, you can just show the correlation functions themselves. So this should just replot again. So here, this is just a plot of just the correlation functions. Or you can plot just the envelopes of the correlation functions. And so this is a better plot to show. This is basically showing, as you increase the channel separation, basically the time it takes the turbulence to propagate between the channels increases. And also the correlation of the turbulence decreases as you increase separation. All right, so now I'll get into those other graphs that are what you actually care about, because those are the graphs that are used to calculate the physical properties of the turbulence you care about. So this first one basically is a plot of the time lag at which the correlation function peaks versus the spatial separation between the channels. So basically, these black data points here, which are the blue data points, which are called group velocity, are basically the peak locations of these envelope functions plotted versus the channel separation. So you can see you get a very nice line, like linear fit to the data, which reflects the fact that the turbulence is propagating uniformly down the array. And by making a linear fit to this data, you can actually extract what the group velocity of the turbulence is. So for example, and it displays it at the top. So for example, it's 6.3 kilometers per second. Also, I should have probably mentioned this earlier, but all of the parameters that are being estimated, so like the delta n over n values I showed earlier, the group velocity and phase velocity here, are all saved to the OMFIT tree in the outputs directory. So if you go under the BES module and you go under outputs, you can see there's folders for cross spectra results derived. So this cross spectra derived holds the delta n over n values, and this cross correlation, so this turbulence parameters folder holds for example, the group velocities we just calculated. So if you want to actually do some other analyses where you're looking at a bunch of shots, you can combine data by just directly accessing it from the OMFIT tree. All right, and so yeah, you can see here there's two plots. There's this blue one is for group velocity. This black one is for phase velocity. The phase velocity is made by fitting to the peak of the correlation functions themselves, which again, I'll just go ahead and replot this real quick. So basically the phase velocity comes from fitting to the peak of basically where these correlation functions peak, and the group velocity comes from fitting to the location where the envelope of the correlation functions peak. And usually for when you're in a regime where, like especially in the core of the plasma where the E cross B velocity is very large, usually those two velocities are very similar. All right, so that's group and phase velocities. The next thing you might care about is the correlation time measurement. Go ahead and plot that. So what this is doing is basically it's taking the the actual y value of these peaks and plotting them versus the time at which they occur. And so you can see this is correlation versus time lag. And so this is and then we fit this with a Gaussian, which usually if the data is high enough signal to noise ratio, high quality, then usually the data follows the Gaussian behavior. And so you can see here basically what this is telling you is as the turbulence propagates to the plasma, it decorrelates with itself over some characteristic time scale. So the 1/e value of this decay, of this core decay of the turbulence for this discharge is about 13 microseconds or so. So that's kind of a typical D through D values are, anywhere from 5 to tens of microseconds, depending a lot on the discharge and the physics that's going on. So that fit is what gives you this correlation value that you care about. And then just to go back to this derived setting, sometimes in rare cases the fit will just fail spectacularly because it's a nonlinear fitting algorithm. So sometimes they just give bad results. So you can try playing with the initial guess. A lot of in my experience, sometimes just using a different initial guess makes the fitting algorithm work a lot better. So usually you shouldn't have to change that, but sometimes you have to do a little bit of manual changing to get the fits to work. All right, so then the last fit is for correlation links.
It's a bit of this kind of connection to theory world here, or turbulence, that typically that decorrelation time is something similar to kind of called the gyrokinetic time scale, like A over CS is a parameter it's often used, or the inverse of a growth rate, which is CS over A is kind of parameterization. Those are usually in the ballpark of each other. So here it's just a number, but it usually connects somewhat sensibly with gyrokinetics.
All right, and then the last turbulence parameter that I'm in here is the correlation length. So here it's plotting the value of this correlation function basically at 0 time lag. So basically how correlated the turbulence is as you increase channel separation. So this is correlation versus channel separation. And once again, usually follows a Gaussian decay if the data has high signal to noise ratio. In this case, the correlation decay had 1/e length scale is about 7.5 centimeters or so. And so, yeah, depending on the physics you're interested in, both of those, all four of those parameters might be of interest to you. All right, so moving up to even more sophisticated analyses.
Presumably you can do radial correlation length too with the.
Yeah, you can do radial correlation links. There's the additional difficulty with radial correlation links of common mode effects. Basically, if you're not careful, you can run into situations where the radial correlation length that comes out of the analysis is much longer than physical, and so usually that requires a little bit more understanding of the diagnostic. So if you're going to do radial correlation links, it's probably best to ask someone from the BES group for help with that, because there's pitfalls there. Okay, I'm actually going to gloss over this analysis because it's basically velocimetry does a better job of what this gives you out. But basically this DTWTD tab stands for dynamic time warping time delay estimation. So there's an acronym in the tab name, but it's written out down here in case you're interested. And basically this is an algorithm that is used for calculating turbulent velocities. So in other words, so this cross correlation analysis I just showed, those phase velocity and group velocities were averaged over very long time scales. So in some sense, it was what is the phase velocity of the turbulence on average over some long time scale. If you're interested in what's the velocity of the turbulence on a very short time scale, so actually if you're actually interested in the velocity fluctuations, then you need to use a more sophisticated analysis like dynamic time warping. I'm going to skip over this because the next analysis, velocimetry, is basically a more sophisticated version of dynamic time warping. And whereas dynamic time warping will just give you the velocity between two BES channels, velocimetry will give you the whole 2D turbulent flow field over the entire spatial extents of the BES array. So this is by far the most sophisticated analysis we use for analyzing BES data. There's only a small number of people in our group who use it frequently. And there's a lot of careful preparation of the data you have to do before you can even start it. So basically this workflow, it has a set of workflows in and of itself. So we're under the velocimetry tab, and you see a bunch of other tabs pop up. So the first step in the workflow, and most of the work goes into this one, is basically generating a set of turbulence images from the raw BES data. And then I have, I'll just give you an overview real quick, and then after you have a set of generated images, you can display them. That's how you can make nice little movies or animations of the turbulence images that we like to show at talks. I like to show at talks at least. Once you have a set of turbulence images, then you can actually apply the velocimetry analysis. That's what this tab does. And then finally, we have another set of another tab for basically post-processing the velocimetry analysis. So see, once you run velocimetry, then you can do more analyses on that velocimetry data, and plot things like flow profiles and even estimate what the Reynolds stress is. So basically, because this generation step requires a lot of time and effort and also takes a long time to run, I'm not gonna like show you an actual running example because it would just take too long. So I'll just kind of briefly go over some of the steps involved. Similar to how for the cross correlation data, I picked one column and I looked at the cross spectra down this whole column to identify frequency ranges where the turbulence is coherent. To do velocimetry, you basically have to repeat that step, but for all the columns. BES. So for all 8 columns, you have to look at cross spectra, identify frequency ranges where the turbulence is coherent, and then you have to basically go through and manually filter the BES channels for each column. So that process takes a while to do. And then once you have all that data filtered, then you can use that filtered data to generate a set of turbulence images. And basically what this generate images button does is it takes the BES data, which is effectively an 8 pixel by 8 pixel set of images, and it spatially interpolates them up to a higher resolution. So typically we use something like 45 pixels by 40 pixels. And that's just necessary for the velocimetry algorithm to run. And so I'm actually going to move over to a different project that already has velocimetry results. I'll just show you them. So this is a different project I'm working on with velocimetry already run. So this is that shot we were analyzing, 171472, same time window. So select that shot, and let's say I just want to show like an image, see what the turbulence looks like for 1 millisecond of that data set. So you can just click animate turbulence images and you'll get a nice animation. So you can see here, these are turbulent eddies propagating upwards. And then you can see over at the inboard side of the array, there's actually slight downwards propagation. So there's a lot of dynamics going on here, but it's a nice little visualization tool. All right, and then you would run velocimetry. The ODP stands for orthogonal dynamic programming. That's the algorithm we use. These settings, the defaults are usually good. You have to spend a lot of time learning how ODP works to change these, so it's not something you should really touch unless you really know what you're doing or just talking to someone.
For this velocimetry, what is a typical time window that you choose to make these images and such?
Yeah, so
What's the order of?
So for my analysis, I've been using like time windows on the orders of hundreds of milliseconds, basically the full time window where the turbulence is stationary, because then I can average over that time window.
Okay. And now when you click that blue button there, how long is it going to take for this hundreds of milliseconds to be performed?
Yeah, so I actually wrote that down. Let's see here. So right now, the velocimetry takes about 5 minutes of runtime for 100 milliseconds of data, which is, so I actually, as part of my graduate work, I've done a lot of work in optimizing this, so it runs faster than it used to. Most of the time in velocimetry analysis is this generation image step. The time it takes to go through all the data, identify filter frequencies, and then just running this also takes a very long time. So that's where most of the time is. All right, so I've already run velocimetry for this example, so I'll just like briefly go through the post-processing. So I have the same case selected with velocimetry results, and you might want to look at a flow profile. So this is a profile of the colloidal turbulence velocity in kilometers per second versus radius, and you'll notice it's the flow is upwards here near the edge of the plasma. Upwards in this plasma is the electron diamagnetic direction. So what you're seeing here is actually equivalent to an ER well. Basically, a negative ER would give you a vertically upwards velocity. So that's what you're seeing. You're seeing the kind of flipped ER well here. And then you can basically, this is the same cross spectra stuff, but instead of taking spectra between the density fluctuation field, now you're taking cross spectra between velocity fluctuations. And I'm not going to actually show this right now because it's a bit of a work in progress and there's a few bugs I have to work out. And then finally, an important quantity for turbulence research is the Reynolds stress, which is the correlation between the radial and colloidal velocity fluctuations. so here's a utility for inferring the Reynolds stress. And so I can just run this real quick, and it'll basically spit out basically a set of time histories of Reynolds stress versus columns. This is the innermost column, and then moving outwards. And you can kind of see in this case the Reynolds stress started slightly negative, and as you move out, it becomes slightly more positive, and then goes back to near zero. You kind of just look at an average sense. And then here's like a profile of the Reynolds stress to the edge of the plasma. So, but most of this post-processing stuff is a work in progress. So
the gradient of this is important to point out, maybe.
yes,
Say something about that.
yeah, the gradient is a physically important quantity because the gradient of the radial gradient specifically of the Reynolds stress, so the derivative of this graph, is a driving force for colloidal flow in the plasma. So, and it's also a driving force for zonal flows, which is important for the dynamics of the LDH transition, which is what I study. All right, well, that was pretty much a walkthrough of all the analysis steps. I went through some of the higher order ones, but really the most important stuff for general audience is really just these first two, just spectrograms for qualitative turbulence evolution, and then cross spectra for looking at the actual spectrum itself and also calculating fluctuation amplitudes, delta and occurrence. All right, so that's the walkthrough. If there's any more questions, happy to answer them. Otherwise, that's it.